Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 2. 4GHz High Gain and Low Noise CMOS LNA Ms. Tanvi Sunil Gursale Department of Electronics and Telecommunication Engineering, Vidyalankar Institute of Technology, Mumbai, India Professor Satendra Main Department of Electronics and Telecommunication Engineering, Vidyalankar Institute of Technology, Mumbai, India Abstract. This paper presents the design of narrow-band single-stage low-noise amplifier, LNA, which is optimized for working in the 2.4 GHz frequency band range. The proposed LNA has been designed and simulated in RF-TSMC 0.18 m CMOS technology by Advanced Design System, ADS. The designed LNA uses 1.8 V supply voltage and it exhibits a gain of 24.253 dB, noise figure of 0.834 dB, input reflection coefficient, S11, of -12.89 dB, reverse gain, S12, of -30.27 keywords Advanced Design Simulation, ADS, Software, Low Noise Amplifier, LNA, Complementary MOSFET, CMOS, Introduction. Due to the tremendous growth is wireless communication technology, the demand for highly integrated radio frequency circuits having low noise, high gain, and low power dissipation is increasing. Wireless systems comprise of a front end and a back end section. The front end section processes analog signals in the high radio frequency, RF, range, while the back end section processes analog and digital signals in the baseband low frequency range. Radio frequency, RF, refers to the frequency range in the electromagnetic spectrum that is used for radio communications. It lies typically from 100 kHz to 100 GHz. However, in general, frequencies below 1 GHz are considered baseband frequencies while those greater are described as RF. The radio frequency signal received at the antenna is weak. Therefore, an amplifier with a high gain and good noise performance is needed to amplify the signal before it can be fed to other parts of the receiver. Such an amplifier is referred to as a low noise amplifier and forms an essential component of any RF integrated circuit receiver. 1. Low noise amplifier is the important and first block of RF receivers. 2. The signal received by the antenna is very small. In order to achieve good linearity, high gain, and low power consumption, it is important to amplify the signal as much as possible without the addition of noise. 3-4. The most optimum trade-off between various parameters has to be achieved for designing of LNA. Also, the size of communication devices and power consumption should be as minimum as possible, which is possible nowadays because of advancements in integrated circuit, IC, technology. 5. Several fundamental low-noise amplifier topologies for single-ended narrow-band design are available, such as resistive termination common source, common gate, shunt series feedback common source, inductive degeneration common source, cascode inductor source degeneration. 6. The design is based on an inductive degeneration common source configuration. This paper describes the operation and the simulation of S parameters, gain, and minimum noise figure using 0.18 m CMOS technology. 2. Device specifications. A DC biasing selection of transistor is essential in the first stage. A CMOS 180 nm technology transistor with TSMC 0.18 micron CMOS logic process technology scale is utilized for realizing front-end designs. This device is biased to operate at VDS equals 1.8 V, IDS equals 0.03 A. The value of gate source voltage, VGS, is obtained from IDVDS characteristic curve, in quiescent point of transistor 7, which is shown in Figure 1. Figure 1 IDVDS characteristic curve. The DC biasing circuit that is employed for the simulation is shown in Figure 2. Figure 2 DC bias network B. Stability. The stability is the most important thing which needs to be considered when designing an amplifier. If stability is not designed properly, the amplifier would get self-excited and it cannot work rightly. Stability can be determined from the S parameters, the matching networks, and the terminations. To improve the stability, a negative feedback is an effective technique is used. The source ground is connected with an inductance to form a negative feedback to improve the stability. It can be shown that the amplifier will be unconditionally stable if the following necessary and sufficient conditions are met. 8. IJERT 10 is 060283 www.ijert.org 625, This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021, 1, 2, C. Matching network. In order to maximize power transfer from source to load, matching impedances is required. The input and output matching networks is designed using Add-Smith chart utility. The open stub matching is used to design input and output matching networks. Proposed circuit provides high gain and low noise figure by maintaining good linearity. 4 simulations and results. Simulations of the proposed LNA for 0.18 CMOS process were performed using ADS. The low noise amplifier provides a gain, S21, of 24.253 dB as shown in Figure 8. The input reflection coefficient, S11, is minus 12.890 dB as shown in Figure 6, and the output reflection coefficient, S22, is minus 19.620 dB as shown in Figure 9. The circuit operation requires 1.8 V power supply. The value of reverse isolation, S12, as shown in Figure 7 is 30.270 dB, and a minimum noise figure of 0.834 dB is obtained as shown in Figure 10. The simulated amplifier's characteristics summary is presented in Table I. From Table I, compared with other LNAs, the performance of our proposed CMOS LNA is much better as it has the best reported value of NF at 2.4 GHz. Figure 3. Input impedance matching. Figure 4. Input impedance matching. 3. Circuit design. Figure 6. Input reflection coefficient, S11, S11, input reflection coefficient, also known as input return loss. It represents the measure of matching of the input impedance to the reference impedance. For 2.4 GHz, as shown in Figure 6, the value of S11 is minus 12.890 dB. Figure 5. Schematic of proposed circuit in ADS. In the proposed LNA architecture employs inductive source degeneration to generate a real term in the input impedance. Tuning of the amplifier input becomes necessary, making this a narrowband approach. The inductive source degeneration is the most prevalent method used for CMOS amplifiers. At the series resonance of the input circuit, the impedance is purely real and proportional to. By choosing appropriately, this real term can be made equal to 50. The gate inductance is used to set the resonance frequency once is chosen to satisfy the criterion of a 50 input impedance. L1 and C1 provides proper input matching, and L2 and C2 provides output matching. Thus, the Figure 7 reverse gain/reverse isolation, S12, S12, reverse transmission coefficient, also known as reverse isolation, it measures how much the input signal is reflected back. For 2.4 GHz, as shown in Figure 7, the value of S12 is minus 30.270 dB. Hence, a high isolation is present between input and output. IJERT 10 is 060283 www.ijert.org 626. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. dB has been obtained at 2.4 GHz, as shown in Figure 10. This value indicates that the noise performance of the circuit is very high as the value of noise figure of the circuit is very low. Figure 8 Forward gain, S21, S21, forward transmission coefficient, also known as forward gain, it measures how well the signal goes from input to output. For 2.4 GHz, as shown in Figure 8, the value of S21 is 24.253 dB. Therefore, the value of output voltage obtained is good even for a small value of input voltage. Figure 11 IIP3 LNA along with amplification of signal and good noise performance, should be linear even when the signal is strong. Hence, during designing of LNA, linearity is an important consideration. The third intercept point is illustrated in Figure 11 that was achieved at minus 9.571 dBm. Table I comparison of different CMOS LNAs. Figure 9 Output reflection coefficient, S22, S22, output reflection coefficient, also known as output return loss, it represents the measure of matching of the output impedance to load impedance. For 2.4 GHz, as shown in figure 9, the value of S22 is -19.620 dB, indicating that a considerable matching of the output impedance to 50 is obtained. Figure 10 noise figure, NF, the noise performance of device at high frequency is indicated by noise figure. The minimum noise figure of 0.834 from the table I, it can be concluded that for 2.4 GHz frequency at 0.18 technology, compared to other LNAs, the designed LNA has least noise figure, of value 0.834 dB, and with a good value of gain, 24.25 dB. So, our designed LNA, in terms of gain and noise, is much better as compared to other reported LNAs at 2.4 GHz. V conclusion in this paper, a 2.4 GHz CMOS LNA is proposed. Good noise figure value of 0.834 dB and high gain of 24.25 dB is achieved, which shows that the proposed circuit has good stability, as obtained at 1.8 V power supply. IJERT 10 is 060283 www.ijert.org 627. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 References 1L Belostotsky and J.W. Hazlett. Noise figure optimization of inductively degenerated CMOS LNAs with integrated gate inductors, IEEE T2 Kuhn Hung Lee and MNL Gamal, a very low voltage, 0.8 V, CMOS receiver front-end for 5 GHz RF applications, 2002 Proceedings of IEEE International Symposium on Circuits and Systems. Proceedings, CAT. No 02CH37353, 2002, pp. I-125 I-128 Vol.13 S. Anirudhan, a 0.6 V 0.85 MW low noise amplifier for 5 GHz wireless sensor networks, 2016 Proceedings of IEEE 59th International Midwest Symposium on Circuits and Systems, Muscat, Abu Dhabi, 2016, pages 1-4. 4 JYH Nanyang, Chenyu Li, Turnyan HSU, Turnren HSU, and Chengchen Wang, a 1.5 V, 2.4 GHz CMOS low noise amplifier, Proceedings of the 43rd IEEE Midwest Symposium on Circuits and Systems, CAT.No CH37144, Lansing, MI, 2000, pages 1010-1012 Vol.2. 5 TH Lee, H Samavati and HR Rayteg, 5 GHz CMOS wireless LANs, in IEEE Transactions on Microwave Theory and Techniques, Vol. 50, Number 1, pages 268-280, January 2002. 6 Derek K. Schaefer and Thomas H. Lee. A 1.5 V, 1.5 GHz CMOS low noise amplifier, IEEE J Solid State Circuits, Vol. 32 pages 745,759, May 1997. 7 Microwave Engineering David M. Posar. John Wiley and Sons. Inc. New York. Chichester. Weinheim. Brisbane Singapore. Toronto Y. 8 Microwave Transistor Amplifier Analysis and Design. Guillermo Gonzalez, Ph.D. 1984 by Prentice Hall, Inc., Englewood Cliffs, New Jersey. 9 A low power, high gain 2.4/5.2 GHz concurrent dual band low noise amplifier, Hossein Khosravi Department of Electrical and Computer Engineering, University of Burjand, Burjand Iran. Khosravi 95 at Burjand.acir 10 high linearity and low noise shunt resistive feedback CMOS LNA in 2.4 GHz ISM band, Aditi, Department of Electronics and Communication in, Delhi University, 2017 Recent development in control, automation, and power engineering. 11A 2.4 GHz Cascode CMOS low noise amplifier, Gustavo Campos Martins Universidade Federal de Santa Catarina Florianopolis, Brazil. Gustavo CM at IEEE.org. 12A 1.3 MW 20 dB gain low power inductorless LNA with 4 dB noise figure for 2.45 GHz ISM band, François Belmez, 978-1-4244-8292-4/11/$26.00 Copyright 2011 IEEE 13S Manjula and D. Selvathai. Design of Micro Power CMOS LNA for Healthcare Applications. In Devices, Circuits and Systems, ICS, 2012 International Conference on, pages 153-156, March 201 IJERT 10 is 060283 www.ijert.org 628. This work is licensed under a Creative Commons Attribution 4.0 International License.